Hello friends, now we start the chapter Wave Optics, and the last article from the chapter Wave Optics is the diffraction. Already we studied the meaning of the diffraction, the bending of light ray at the edges of obstacle, and entering into the region of geometrical shadow is called as a diffraction. Now when you study the diffraction, then there are the two types of diffraction. One is the Fresnel type of diffraction, and second one is the Fraunhofer type of diffraction. This is already studied. In a Fresnel type of diffraction, cylindrical or spherical wavefront is used. In a Fraunhofer type of diffraction, plane wavefront is used. Slit, source and screen are at a finite distance in Fresnel type of diffraction. Source and screen are at an infinite distance at the Fraunhofer type of diffraction. Today we discuss the Fraunhofer diffraction due to the single slit. So the title, today's title is Fraunhofer diffraction. What is the Fraunhofer diffraction? The first thing is very clear that in a Fraunhofer diffraction, the source and screen are at an infinite distance. If I say the source and screen are at infinite distance, means in a laboratory we can easily observe Fraunhofer diffraction as a source of light as a sun rays. Okay, because the sun and the screen in our laboratory are at an infinite distance. Means source is situated at an infinite distance. Therefore, the wavefront used in a Fraunhofer type of diffraction is a plane type of wavefront. Okay. Now, these are the plane light rays. This is a plane wavefront. The light rays are emitted from source, which is at infinite distance. These are the light rays. Okay. Such a light rays are incident on one edge of the obstacle. Obstacle means a disturbance. We are using a one slit. This slit is my obstacle. Okay, this is the slit. Now label it AB is my slit, and the width of the slit is small a is the width of the slit. Just I label here width of slit AB is the small a. These are my plane light rays. Just we consider only the three light rays which are sufficient, because if this light ray is incident on the part B of the slit, then it is opaque, so no light transferred to this side, and we are getting the shadow. Also here we are getting the shadow. Now this is my slit. Are you getting this? And the screen and the sources are at the infinite distance. No doubt about here. Now the next one. In the diffraction, there is a bending of the light ray takes place. Already bending of light ray takes place in refraction also, but for refraction the light ray changes its medium. But there is here only a homogeneous medium. There is only one medium, single medium. Without bending, the light ray travel this path. The light ray travel this path and falls on the screen. And the light ray travels this path and falls on the screen. Here there is no meeting or no gathering or no interfere of the light rays. Here I am using the plane wavefront. The light rays are parallel to each other. Therefore, I am using a one biconvex lens. This biconvex lens, purpose of this biconvex lens, it converges the light. Okay, biconvex lens converges the light. Therefore, without bending light ray is incident here. Okay, the light rays travels in this path, and here the light ray bend and it follows here. This light ray travels, enters in the lens, and again it converges and falls here. And this point P, here all the light rays are meet. Okay, and here all means there is an interference of this light ray takes place, and that point P where all the light rays are meet, therefore this point P is my central maxima. Why I say this point P is a central maxima? Because here all the light rays are meet, and at this point P we are getting the maximum intensity of the light. Therefore that point P is my central maxima. Suppose the light ray is incident at the point A, and from the A the light ray is diffracted. The light ray is diffracted means what? The light ray is bent. Therefore this is the light ray which is bent. This second light ray is also bent. This is not incident on the obstacle, but it will be incident on what? I am using a plane wavefront. Wavefront is in the wavefront there is a number or bundles of the light rays. Therefore all the wavefront is bent, means the light rays are also bent. And again it travels to this distance, it will be bent, and this light ray will be bent. And all the light rays are false at this point. Like this is my P0, that is my central maxima. So I am writing here central maxima is P0. And now there is a one point P. Okay. Now see here everyone. This is my plane wavefront. Yellow color lines are the diffracted light rays, and the white color lines are the undiffracted light rays. Or the yellow are the bended rays, and the white ray are the plane or travel in a straight line path. Such rays are there. Okay, here the light rays are incident. In between such rays, the angle is theta. In between these light rays, the angle is theta. Now one simple question is that the yellow color light ray travels a one path, okay, and this white color light rays travels a one path. Is the both light ray travels the same path or the different path? Obviously both the light rays travels the different path. How? That we have to see. Both the light rays are emitted from the point A. So I will show by one simple diagram. This is point A. Okay, this is a one. And secondly, this is the bended light ray. Okay. Now both travels the different paths. Then what is the actual path difference that we have to calculate? Let this will be the point M and this is the point N. What is the path difference? Easily someone find out the path difference in way. First he measures the AM, then he measures the AM, and then he writes the path difference equals to AM minus AM. This is the path difference. But some students do in this way, draw one perpendicular at this point. Okay, let that point it will be the O, and he says path difference is equals to ON. Yes or no? This is my simply path difference. So here also I am calculating the path difference. To calculate the path difference, draw a one perpendicular on this diffracted beam at the point M. Okay, AM. Are you getting this? And this distance VM is my path difference. So I am writing here my path difference is BM. BM is my path difference. Now see very clearly. Okay, I will draw the same diagram once again here. Okay, so we understand. This part is clear for everyone. So I am erasing this part. Drawing the same diagram here. This is A. This is okay. this angle is theta. This is perpendicular. So this total angle is also 90 degree. If it is 90 degree, this total is also 90 degree. See very carefully, or I will draw in this way. This is 90 degree. Okay. This angle is theta. Total angle is 90 degree. So this is my 90 minus theta. Are you getting this? This is a 90. This is 90 minus theta. So this obviously it is a theta, because total measure is a 180 degree. So if it is 90 minus theta plus theta, so it becomes a 90. 90 plus 90 is a 180 degree. So this angle is my 90 minus theta. The major thing is that upper surface or upper angle is my theta. So in writing here, this angle is the theta. I think this is clear for everyone. Yes or no? See once again. I will wait for some time. I am waiting for some time. Now tell me, is it clear for you? Yes? Okay.